today. You're welcome to today's lecture. We'll be looking at two things to pretty much end our discussions on the analysis of beams in terms of the external reactions and also the internal loadings. All right. So just a quick recap. All right. So over the past few weeks, we have been looking at what's the name? How to determine reactions. All right. Then also how to draw the shear force and the bending moment diagram. All right. Let me see BM diagrams. Okay. So at this point, confidently assume, or we can agree that we have a good understanding of some of these approaches, right? The TA has done a good job. She's taking you guys through pretty much all of these, how to determine reactions, how to determine shear force values, and then bending moment values as well. She has also taken you guys through what's her name? Uh, the diagrams also. You should have an assignment today on I think these subtopics. Yeah. All right, we'll discuss some other things towards the end of the class. But for now, let's just go ahead and then look at what we have for today. So we just discussed a few things to complete this part. All right. And for today, I wanted to look at internal hinges, right? I think I briefly mentioned that during one of the lectures, or maybe at the early part of the course, all right? So there are some cases, all right, where, for example, if you have this system, it doesn't matter whether it's a roller or a pin support, right? So if you have this system in here, that is what we call a propped cantilever. Okay. So let's say if you have a house, right? Okay, let me just use this as an example. Then you have the balcony sticking out. All right. Usually, if this is how the whole thing looks like, then the balcony is simply um, a cantilever, right? So the wall becomes the support. Oops. The wall becomes a support, and then the extension where we stand on outside the house becomes the beam, all right? So this becomes the cantilever. In some instances, um, depending on what the design considerations were, you would have a column sticking out all the way to the base. All right. So even though let me call this NA, even though the long wall here, it's the cantilever support. Now you have a new support B. Let's say this is a column. Okay, and then this is the wall. Okay. So we can then add the column over here as an additional support system. All right. And this changes the cantilever into what we call a propped cantilever. Okay. Now now the question I have for you guys is, if this is the case, is this structure statically determinate or indeterminate? All right. And if it is indeterminate, what will be the degree of determinacy? Can someone tell me through the charts whether the propped cantilever here is determinate or otherwise? And if it's not, what will be the degree of indeterminacy? Right. So I'm waiting for one or two answers, and then we can continue from there. All right, so based on your answers, it's statically indeterminate to the first degree. All right. And the easiest way to look at it is to determine what your support reactions are. All right. So in this case, there are four unknown reactions. All right. And then definitely we have three equilibrium equations. Okay. So unknown reactions. Great. So because R is more than E, then this is statically indeterminate, right? And then the degree of determinacy will be the difference between the two. So 4 minus 3 will give me 1, which will give me the first degree of the other name. The degree of determinacy is 1. All right. So this is statically indeterminate, right? Great. So basically what this means is that we do not have all the necessary tools that we need to solve this particular problem. It doesn't mean it cannot be analyzed. It simply means that we need some other equations. Those equations, you start looking at them in second year. But we call these equations, we need both the compatibility relations or conditions. They also need the Mimar forced deformation relations, in addition to the equilibrium equations to be able to determine statically indeterminate structures. Okay. So here it means that we cannot solve it as it is. All right. So there are certain structures whereby um, we place a hinge. So we know what a hinge support is. So this is a typical hinge support. All right. But then what we do is that when it comes to internal hinges, we have the beam all right. All right. Then in an attempt to connect the beams to other beams, we place, so I'm going to show this with a round. So we place a hinge, but the only difference is that this hinge here is actually part of the beam. It is not separate. All right. Uh, this hinge over here, the support hinge, is separate from the structure, right? It could be a column, it could be the ground, or it could be another beam. All right. So they are separate. But when we take an internal hinge, it is part of the structure. It is part of the beam, right? It is part of the beam mechanism. Okay, I'll give you some examples and then we can look at it, right? And we also know that when it comes to hinges, there are the allow rotations, right? Hinges allow rotations, and this means that what they have no resistance to rotations or to moments. All right. So which means that um because they have no resistance to any like rotations, then it means that the moment at hinges is equal to 0. All right. We have already discussed that. If you're looking at the support hinge, you would realize that when you are drawing the Mendeleev diagram, as long as the support hinges um, at the ends of the beam, you see that it gives you a 0 moment value. All right. So that's something to take note of. So in the same way, whether it's an internal hinge or an end support hinge, the moment at those points would be 0. Right. Um, so we used internal hinges for a variety of reasons. One of them is that we used to connect two beams, and I'm trying to explain. So we connect two beams or more. Uh, And the idea is that we want it to behave so that at certain point along the beam, the moment will be zero. All right. So one, let me put that into writing. My eraser is not working. Okay, great. So internal hinges are used to connect, what's the name? Two beams uh, in such a way that the transfer of moments is negligible. Okay, means that it is zero, right? Okay, so it means that at this point, um, okay, let me just finish writing that. And also, we use that to also reduce the indeterminacy, which is what we want to accomplish here. The indeterminacy, my spelling is wrong, of a beam or a frame or whatever structure it is. Okay. So in the case of the point two, we can look at the propped cantilever again. You can't see my writings as in bad handwriting or it's not showing or which is which. If it's bad handwriting, please let me know so that I can rewrite them in a nicer way. James, is it bad handwriting? Okay, so let me just rewrite this. Okay, thank you. So used to connect, I hope this is clearer, two beams uh, in such a way that the transfer of moment is negligible. I hope this is better. Sometimes the handwriting just doesn't work. And also reduce the indeterminacy of a structure or of a beam. Okay, all right. So this is like the reasons why we need the beam. So let's say if you go back to the propped cantilever, right, which we had to be like that. Okay. Now to convert this prop cantilever into what's the name? A statically determinate beam, it means that I'll need an internal hinge, right? So once I place an internal hinge, I've been able to convert this particular prop cantilever into a statically determinate structure. All right. So this is what happens. Your unknown reactions are still three. Sorry, are four. So let me label them, maybe just for emphasis sake. So this is A, B, and C. All right. So this is our VA, our MA, HA, VB. So we have four unknown reactions. Okay. We still have three equilibrium equations. Equilibrium. Okay. But because we have an internal hinge right here in the space, what this internal hinge does is that it helps to introduce an additional equation. Okay. So every internal hinge that we have in the system adds a plus one. All right. So it means that if you have two internal hinges, that is plus two. If it's three, then it's plus three, and it keeps going on, right? So this plus one here is coming from the internal hinge, or one internal hinge. Okay. So in a way, it makes this equations equal to 4. All right. So the three equilibrium equations plus the one additional internal hinge, and that becomes 4. And now if you compare these two 4 values, you realize that then 4 is equal to 4, and it makes the structure statically determinate. Okay. We have learned that if you have a cut section, okay, so when you cut your beam along, let's say along this section, for example, so let me call this XX. If you cut your beam along XX, this is what you see, right? You would see the separation of the internal forces, right? So that if you have this end being the left-hand side, and then this other end being, let me just show this with a different color, and this being the right-hand side, you would realize that you do have all of these, um, all of that, and then you also have the moment. Okay, this is what we always experience, right? So we have all these internal behaviors. Now, let's say we cut the section at the hinge. So right at where the hinge is. So this is, let's say, YY. Let me call this section XX. Now, if you have a cut section at YY, okay, pretty much where the internal hinge is located. Now, this is what we would see. So I have my, okay. So pretty much this is where you have our antenna hinge. Let me just show a little bit of it here. A little bit of it over here. All right. Now you would have these forces, but what? No moment. Okay. So no moment, which means that at the internal hinge location, this moment, which I drew with the green color, would be 0. All right. So where you have an internal hinge, the moment at those points is 0. All right. And this helps us to break our beams or our structural members into different sections and then solve them without much struggle. We'll look at an example. We do find this being used a lot in bridge construction. All right, where we try to use this whole internal hinge behavior. Okay. Let me just draw a schematic of that. Let's say we have some valley, right? And then maybe in the valley we have some water, so maybe it's a stream or lake or whatever, right? And usually we want to construct a bridge over it. Water is not really, want to construct some bridge over it. Normally you would have what you call the piers or the columns. So these are the columns running through, maybe we should go a little bit up. These are the columns running through all the way to the base of your river or your lake or your water body, right? So you would construct what's the name? So there's the so we call this the pier, all right, or maybe the column. But usually when they're that long, they are called piers, all right. Um, then you have your deck, which is what will carry the cars or whatever you want to use to cross the bridge. Okay. But then we need to connect the bridge to the mainland, right? So maybe let me see if I can get this thing cleaned up a little bit. So we want to connect the bridge to the mainland so that vehicles can go over. Let me just redraw this, maybe something like this. All right. So what we'll do is that we need to have some connection to the land. All right. And then this portion, let me just change the color. Oops. So this portion that sits will sit right on the ground. All right. And then we'll have some support or some foundation for it like this. Some foundation that goes straight into the ground. And we call this foundation the abutment. Okay. So the same thing on the right, I'll have something similar on the left. So again, I'll join this to the ground, then have the abutment as the support. Right. So these are abutments and the action that support. Okay. So with bridges, they have to be allowed to expand and contract. Reason is that why not all the cases, but some cases you want it to expand and contract because if, for example, you are using steel members as your bridge, you want that option because if you do not allow expansion and contraction of the bridge, uh, for example, if there's an increase or a reduction in temperature, all of these things can happen. You would want to ensure the expansion, otherwise stresses will be built up in your bridge and these can lead to cracks in your bridge construction or the bridge usage, right? So here, how do we join these two ends? All right. How do we join these two ends? Okay. We place internal hinges. Okay. So, oops. So these are internal hinges. All right. So sometimes you might see certain bridges and oops, see certain bridges, and then this is how they look like. You could have maybe it looks something like this way. Then there is a portion looking like that. Okay. So this connection over here, this connection, this zone, oops, connection this zone is actually an example of an internal hinge. Okay. So it's quite common in bridges. And what it does is that it takes this whole system as we see it, and then it converts it into a statically determinate structure. Okay. If I'm to draw the analytical model of the bridge system, what it means that I would have, so I have, so this is my bridge, this support is my abutment. So maybe let me put it this way, maybe let me put, first, maybe let me fixed. So this is the abutment, I have the column, the other column or the pier. They also have the other abutment at the ends. All right. So these are the abutments. This is also the abutment. Okay. And then we have these two guys here being the pier. All right. So here, this is statically indeterminate. To what degree can I get an answer? What degree of indeterminacy do we have for this particular structure? It's statically indeterminate that we know, but I would like to know the degree of indeterminacy. Someone says 5. Any other answer? Okay, so it's 5. All right. Of course, we have how many unknown reactions? We have 1, 2, 3, 4, 5, 6, 7, 8. So 8 unknown reactions. The equations are what? 3. All right. So E, so to the 5th degree. All right. We can, in a way, try to reduce this. All right. Maybe I should have gone with the other option, but it's fine. It's fine. All right. Doesn't really matter. I'll explain why I'm going with this option. So in this case, now I'm trying to change all of that. So I take all of this and then redraw that here. Let me delete this, guys. Okay. Now I have an internal hinge here, an internal hinge over there. So what now becomes our degree of indeterminacy, for example? I mean, degree of indeterminacy in this case, we still have our 3 equations or our 8. We still have our 8 unknown reactions. We have our 3 equations. Now we have 2 internal hinges. So what would be our degree of indeterminacy in this case? To the 3rd degree. All right. To the 3rd degree. All right. So it means that our total equations now becomes 3 plus 2. And this will give us 5. And then our reactions is still 8. So 8 minus 5 will give us 3, which is the 3rd degree. Right. So we have reduced the degree of what? Indeterminacy. All right. And under this condition, it's actually what's the name? We can break it a bit more. You can break it down and down and down, add a few more, what's the name? A few more hinges, and then we could keep reducing and reducing, right? So this is the general idea of why we need hinges, right? It's sometimes it's to reduce the degree of indeterminacy and then make our structure easy to analyze. Okay. If, for example, the abutments were pin supported, all right, then this becomes an easy to do problem, right? Because then once we indicate the 2 internal hinges, then we should end up with a statically determinate structure, all right, in the end. So let's see an example of what we've been looking at so that we appreciate it a bit more. So I will deal with prop cantilever. There are other examples that we can look at. I'll go with this here. So I have a beam. Let me place the internal hinge somewhere here. So that's my internal hinge. Okay. And typically, this is how I would represent internal hinges to you guys. It's going to be around maybe shaded circular shape uh, inside the beam. All right. So we have these dimensions. Each one is 4 meters. Okay. And I have a UDL which sits right from the internal hinge to the support at the very right. Then I have a load maybe somewhere here, a point load. Let's say this is 10 kilonewtons. Okay. So let me label this as A, B, C, and D. All right. So now let's find out if this last structure is statically determinate or otherwise. All right. So this will be our support reactions. So we have VD, VA, MA, HA. All right. So again, our unknown reactions will be what? 4. Our equations will be 3, and then we have 1 internal hinge. Okay. So by virtue of that, we have 3 plus 1 equals 4. And that means that since our equations, our total equations in quotes equals our reactions, then this particular beam is statically determinate. Okay. So to analyze such a beam, we break the beam into 2 parts. Okay. And we break it at the internal hinge location. All right. So that we'll end up with 2 parts. Oops, what's happening? Okay. 2 parts of the internal hinge. And let's see. So we have oops. Let me exaggerate it a little bit so that it helps us. So we have part 1. So we have a support here. We have a support over here. We have a UDL, right? Why not changing to yellow? Understand I started. Okay. Sorry, sometimes the whole thing just goes haywire on me. So we are solving a problem. Let's continue with it. The reactions are 4 because someone wants to know why the reactions aren't 5. They are 4 because the fixed support reactions aren't 6. Now I'm lost. Okay. The internal hinge is part of, I think it has to do with the internal hinge, right? The internal hinge is part of the structure and it's not a support, right? So because it's not a support, it cannot add to the external reactions. Okay, and it's part of the beam. It's not a support. An internal hinge can be seen as like, if you're looking at a human body, it can be seen as our knee joints, right? The joint in our knee, for example, right? Because that's how we're able to move our knee, our legs back and forth, right? Not sideways, but back and forth, right? That's pretty much our knee joints rotating. So that's a typical internal hinge. And it's not part of your support. The support would be the ground on which you are standing. All right. So we can see it in that form where the internal hinge is part of the beam. It is not a support. Okay. So it doesn't add up to the reactions. They are to the unknown reactions. Okay. Just that with an internal hinge, it can allow rotations. All right. Just like our knee joint, which can rotate, I mean, about the joint. All right. But then so no rotation. I mean, it doesn't have what's the name? It doesn't have resistance to rotation. So the moment at that point is 0. Okay. Hopefully this explains it. Okay. That's like how we only have four reactions in this case. So, but once you break your beam into two parts at the internal hinge would then have these unknown reactions. Okay, they are not reactions per se, as in external reactions, right? We could call them internal reactions. So at least maybe we separate our minds from the two. Okay. Then we have the main external reaction, VD. So let me call this one VC and HC. All right. Then we have a UDL on top. Okay. With a 2 kilonewton per meter load. The reactions, the 10 kilonewton load and then the UDL are not reactions. They are loads. All right, or they are the actions. All right. Newton's third law says that what actions and reactions are equal and opposite. So the actions or the loads acting on the beam are the 10 kilonewton load and then the UDL. We don't add them to the reactions, right? The reactions are coming from the support system, okay? And supports can be the ground. It can be another structural member like beams or columns or slabs or whatever. All right. I'm hoping this explains that to us. Loads are not reactions. Loads are loads, and reactions are coming from the support conditions. Okay. So we have that. So this will give us. So this particular part of our beam, this section here, is statically determinate. Okay. So with this, we can go ahead and solve for the right-hand side. But before then, let me do the left-hand side. Let me complete that one as well. So I have here my 10 kilonewton load. And one of the easiest ways that I've found is that when you're putting the forces on whichever side you decide to go with, whatever you put on one side, you put an equal and opposite on the other side, okay? So on my right-hand side, HC is going towards the right. So I can make HC go towards the left, okay? On my right side, VC is going upwards. So on the left-hand side, VC will go downwards, right? Again, when you sum these two things up, they should give you zero. Okay. Pretty much that's what we'll be trying to do when you try to cut a section, right? So we have left-hand side, left-hand side, and then right-hand side, okay? So let me just put some break in between the two, okay? So we can solve the right-hand side easily, or not easily, but we can just solve it. VC plus VD, since we are summing all vertical forces, VC plus VD will be equal to 2 times 4. The distance here is 4 meters. So that will give us 8 kilonewton. And then when you solve this, you would see that VC is equal to VD is equal to 4 kilonewtons. Okay. Our HC here will be 0. Okay, I'm jumping a few steps because I believe that at this point we all know how to find reactions or support reactions. Okay. So whatever we get for VD, the same as VC, at least for the right-hand side. So it means that our VC here is 4 kilonewtons. Our HC is 0. All right. So with that, we can come and solve the left-hand side. We have this as our known reactions. So HA, MA, and then VA. So at least HA is equal to HC, and that will give us 0. All right. Then we have, when you're summing vertical forces to be equal to 0, We have VA upward minus 10 minus VC equals 0. So VA will be equal to 10 plus 4, and that'll give us 14 kilonewtons for VA. Okay. Now let's sum moment about A to be equal to 0. So we have MA, which is a clockwise moment, minus, what's the name? Minus the 10, sorry, plus, because they're all clockwise, 10 times 4 plus VC times 8. So these are the distances that I'm trying to work with, 4 meters and 4 meters, all right? So all of this should be equal to 0. So when you sum this up, our MA will be minus 52 kilonewton meter. 10 times 4 will give us what? 40, I believe. And then VC is 4. 4 times 8 is what? Am I correct? Someone can confirm my answer for me if I'm right. 10 times 4 plus 4 times 8. Oh, 72, sorry. Great. Okay, so 72 kilonewton meter. All right, so this becomes our bending moment value. And then, so it means that if I want, I can come back to the original structure as I had in the very beginning, and then add my internal hinge somewhere here. So now I know my reactions, right? I know my reactions now. This is 14. This is minus 72. And this here is 4. All right. So from here, I can draw my shear force and bending moment diagrams, right? So I still have my loads on top. 10, and this is 2 kilonewtons per meter. So I have my loads. And let's see. Yeah, so let's draw a shear force diagram. Okay. So I'll jump a few steps because I believe that at this point we know how to draw a shear force diagram. Okay. So the shear force at A will go to 14. It remains 14. And then at B, it comes down to 4. It remains 4. Then because between, so this is A, B, C, and D. But between C and D, we have a UDL, so that would give us, oops. So this becomes our shear force diagram. So then put in the values. This is 14. Here we have 4. And we have 4, right? So this is our plus and this is our minus. Okay. If you have any questions, please ask. Then with our bending moment diagram, again, the same process. So this is your A, B, C, and D. So I have my A, B, C, and D. All right. So our bending moment value here, so this will be a negative value, all right, of 72 because it is a hugging moment. And then at B, this will jump to what would be the value? So I'm jumping a few steps, all right, because we already know how to do some of these things. So we have 72 minus 72 plus 14 times 4. So this will give us 16. So here will be minus 16. All right. Then at C, here will be 0. Okay. And I'll show you why it's 0 shortly. All right. Then between C and D, this is how the diagram will look like. Oops. With the top value here being WL squared over 8. So 2 times 4. So here, this value here is 4. All right. And this coincides with where the shear is 0. I think the last time we met, we explained that where the shear force is 0, it means that at that point you will have your maximum or minimum bending moment value. Right. So let me explain why C is 0. Okay. Um, so pretty much bending moment, the bending moment at A is equal to MA, okay, which is equal to minus 72. Bending moment at B, so here I'm doing that from the left towards the right. It becomes MA plus VA times 4, okay? So this will be equal to minus 72 plus 14 times 4. That'll give me minus 16 kilonewton meter. Okay. Now the bending moment at C is still MA. Please, this MA here is actually a point moment. So please take a note. The reaction moment for a cantilever is pretty much a point moment. Okay, so it becomes MA plus VA times 8 minus the 10 times 4, and this should give us 0. So this becomes minus 72 plus 14 times 8 minus 10 times 4, and this should be equal to 0. B is not 16, B is minus 16. B is minus 16. Okay, so let me see if I can explain this again. So we know that if you want to find the moment at B, you cut your section at B, right? So if I have my, so let's say on this, let me say aside, okay, no, this might not be enough. All right, so let's say I have this here. So I'm just taking, so here you cut your section at B. So we want to find bending moment at B. All right. We have these, we have our MA, we have our VA. All right. So we know that these are our sign conventions. This is positive. And then if you have this here, this is negative. All right. So our VA is on the left of B. Our MA is also on the left of B. So bending moment at B will be equal to. Now let's look at this direction, and it's a clockwise direction, right? And it's on the left. So it's the same as this guy over here, right? So it's supposed to be a positive, right? Which is fine. So it becomes MA. Oops. So it becomes plus MA. Let's leave it this way. Then the moment caused by VA about B would also be clockwise, right? So plus VA times whatever that we have for the distance. Okay. But please take note, MA in itself is negative, all right? So this is equal to what? Plus into brackets minus 72 because MA is negative actually in terms of its value and its direction, plus a VA where V is 14. So 14 times 4 And if we do that, minus 72 plus 14 times 4 will give us minus 16. And that is the reason I had the minus 16 in my previous calculation. So this is just an aside to explain the concept to us. All right. Then we can also find the bending moment at, so let me call this point here, the middle point here, let me call this point K, where K is half the distance, just to explain that to us. So bending moment at K will be equal to, again, MA minus VA times 12 minus 10 times 6 minus, what again do I have? Minus the UDL, which is 2. So 2 times 2 times 2 over 2. And this will give us 4 kilonewton meter. All right. Then the bending moment at D will be equal to 0. All right. And the way we can find that would be MA minus VA times, no, this is supposed to be 10, not 12. VA times 12 minus 10 times 8 minus 2 times 4 times 4 over 2. Okay, and this should give us 0. All right, you can play around with this, okay? Just play around with it. Is this the same as what we've been looking at so far? I only wanted to show you guys that when you have an internal hinge and you are drawing the bending moment, always, all the time, at where the internal hinge is located, the moment goes to 0. All right. It is that's what an internal hinge is there for. Okay. So this is an example. I'm sure maybe you can do one or two more in your tutorials this week. But that's what internal hinges are there for, to explain, I mean, pretty much. So once we come across internal hinges, we should know what to do with them. Now let's look at frames briefly. We won't spend too much time over here. Okay. So a frame, usually it's a combination of beams and columns. Okay. We all went to the field trip, I believe, I mean, the past week, Friday or so. So we all have seen what columns and what beams are. So now if I say columns, I say beams, and I say slabs, we should all know what that is, right? Or we don't know? I believe we do. Okay. So we've seen frames, we've seen columns, we've seen beams, we've seen concrete, we've seen steel, we've seen timber, I think so. Right, so now we have an idea, or now we can visualize some of these terms when I use them. Okay, so let's say I have a column. So this is a column, right? And maybe there's a fixed support on the column, and I have a beam attached to the column, right? So something like that. Okay, so this is A, B, and C. This frame here is statically determined, right? We can have different frames. This is also an example of a frame, right? Some even come with extra information. So these are just different frames, right? And basically, the building you guys went to, I think at, what's the name? Roman Ridge in Accra, is pretty much what we call a frame system, right? It's designed with the columns and beams acting as frames. Was it a beam? Is it a conventional beam, slab, column arrangement or slab beam column arrangement, or it was a flat slab? Was that mentioned to you guys at the trip? Do you know whether it was a conventional beam, I mean slab beam column arrangement, or it was a flat slab? Anyone? All right. So we have this also can be a type of frame, right? These are just frames. Could also have another frame looking like this. Maybe something like that, right? So we have different types of frame systems that we have. Okay. Particularly, it's a combination of either beams and columns or even slabs and columns. Okay. So now let's look at our example. So we have a frame, and on the length of the column, we have some loads. All right. This could be a wind load. Okay. Wind tends to act laterally on the face of a structure. So let's give this wind load a value, let's say 2 kilonewtons per meter. Then we also have some other load on it. So this is a typical trapezoidal load, which I think we have not really spent too much time on it, but at least we can do that with this example. Okay, so the first is, or the smaller portion is 2, and then the larger portion is 5 kilonewtons per meter. And the distance is here, or the length of BC is 9 meters. The length of AB is 15 meters. All right. So let's say find reactions. All right. So our unknown reactions will be 3 because we only have one support. Okay. Take a note, this here is a joint, right? It's a joint, not an internal hinge. Okay. It's just a joint, right? That's all. Okay, not an internal, it's just a joint to connect the two members together. We've not purposely placed an internal hinge over there. When we do this, yeah, now to mention, when you have a statically determinate structure, like in this case, and you place an internal hinge in there, you make your structure unstable. All right. So for example, let me just uh, sidetrack small. If you have this beam here, right, this is statically determinate, right? And you should place an internal hinge over here. It means that your unknown reactions are 3. Your equations are now what? 3 plus 1. And since E is more than R, this is unstable. Okay. And what this means that if you should apply any loads to the system, I'm sorry, to the system here, it would undergo a mechanism, right? So you have your beam go this way, right? It just bends down like that, and then failure would occur. All right. So when we are adding internal hinges, we are careful as to how to add them so that we don't end up creating some failure mechanism. All right. All right. So let's go back and then solve our problem. So let's find reactions. So these are our unknown reactions. This is HA, VA, and I want to find MA. All right. So let's look at it. With HA, we are summing all horizontal, sorry, HA, we are summing all horizontal forces, and there are two of them. Um, so I had explained to you guys that if I want to show you guys an internal hinge, I would actually, you'll see that my drawing, okay, I'm coming, sorry. Some want to know why, or the difference between an internal hinge and also, what's the name? A joint, right? Typically, if I have this here, right, this point is a joint. It's just a joint, joining two elements together, and that's about it. And usually, if it's a concrete structure, we'll join them using, what's the name? The rebars will join together. If it's a steel structure, we can use bolt or nuts or uh, welding in there. And that's the joint. Okay. If I want to have an internal hinge, at least for the analytical models, I would place, what's going on? Okay, actually place a circular point here like this, which is to indicate to you that this is an internal hinge. Okay. Okay. So let's take a note of that. Okay. An example, let me see if I can find a picture of it. And picture of an internal hinge. Let's see. Hopefully I can find one. Uh, okay. It's giving me something interesting. Um, in the structure, maybe let me just do increase more. It's not a very common thing that you see being used. I'm looking, you find it normally in bridges. So hopefully I can find one. Okay, I'll keep looking. Okay, I think I found one. It's not the clearest of pictures, but uh, pardon me. Let me see if I can copy that. Copy image. Okay, let me show 155. Where are you guys? All right. So can we see, so this actually, what's the name? An arch, right? A pane arch. Okay. So here we'll look at arches very soon when we get to, I'm sure in the next two chapters or so. This is an arch. And then here is the internal hinge, as we can see. So this is an internal hinge. Okay. So I'm hoping this picture is, makes things clearer a little bit. Okay. All right. So let me push this one down a little bit so that I can have space to do what I want to do. Okay. Hopefully, I've answered all your questions. We'll take some 5 minutes break after this, and then we'll come back and then continue. All right. So if I submit all horizontal forces, then it means that our HA here, HA plus this load here is horizontal. Okay. So convert this UDL into a point horizontal load. All right. So it becomes HA plus 2 times 15. Okay. Then put it to 2 kilonewtons per meter times 15 meters equals 0. All right. So means that HA will be equal to minus 30 kilonewtons. Now let's sum vertical forces. So here we do have VA minus, again, this is your vertical force right here. Okay. And this is a trapezoidal load, right? So you have options on how to solve this particular problem. If you have a load that looks like this, okay, this is 2, this is 5. The length here is 9 meters. Is what an area of a trapezium is what half A plus B times H, right? So here, this is your H, this is your A, and this is your B. All right. So it can be VA minus half of 2 plus 5 times 9 equals 0. So VA here will be equal to, what did I have? 31.5 kilonewtons. Okay. Now let's find the moment. So let's say let's sum moment about A to be equal to 0. Okay. Now that's the interesting part to this problem. All right. So if we take moment about M to be equal to 0, so we have our MA, which is a clockwise moment. And then the wind load, assuming it's a wind load, the yellow shaded load will also cause a clockwise rotation about A, right? So it becomes plus the 2 load times the 15 times 15 over 2. All right. Then plus this other load over here. The easiest way to solve this particular problem, so I'm going to break it here. The easiest way to solve this problem over here is that if you have this as your load, okay, break it into 2. So you have this portion right here, okay, being 1. So this is area 1. Then it becomes your area 2. So the area 2 will be the shaded region right here. Okay. So what this means that this height is 2. This height is also 2. And then that will leave this remaining height to be what? 3. Because 3 plus 2 should give us the 5. Okay. And then this our distance here is what? In this case is what? Is 9 meters. All right. So usually what I would do is that I'll solve area 1 and area 2 separately. All right. So if I'm dealing with area 1 or with section 1, then it becomes 2 times 9. I don't usually like to bring times. So 2 times 9 times 9 over 2. And that'll give us our moment. And then plus, then, so this is for area 1. And for area 2, it becomes half, because a triangle, so half base. The base is 9 times a height of 3. Then the moment arm would be 2/3 of 9. Yes, it looks a lot, which it is though. Let me just do it this way. 2 over 3 times 9. Okay, this is better. Right. So all of these should be equal to 0, and they're all clockwise. They're all clockwise. So just take note. So this becomes MA plus 225 plus 81 plus 81 equals 0. So the MA here will be equal to minus 387, I believe, kilonewton meter. Okay. So let me go over the sum of vertical forces, and I'll go over the moments as well. Okay. So again, we are summing forces or moments or whatever. Look at the ones that that would contribute to whatever you are trying to do. Okay. So that if it is moment, or if it's, sorry, if it is a vertical load, your VA as well as the top trapezoidal loads are your only vertical loads that you have. Okay. So in this case, we want to sum VA here and also these loads. Okay. But this is what we call a distributed load. All right. So we need to convert the distributed load into bracket a point load to find the area of that load. Okay. So since it is a trapezium, we find the area of the trapezium. Right. When the distributed load was a UDL, you found the area of the UDL, right, by multiplying the height times the length, which is area of a rectangle. Okay. So if it is the area of a trapezium, it is what, half A plus B times H. Okay. That's the equation that we know for finding trapeziums or trapezoids or whatever. Okay. So here your A is your 2 meters, sorry, your 2 kilonewtons per meter, and then your B is your 5 kN per meter, and then your H is your 9 meters, which is the length of the rectangle, sorry, of the trapezium. So once you find that area, that'll give us 31.5. Okay, and then that would equate to VA. The other way to look at it again, if since we broke this guy here into two, I can find the area of the separate parts. So for part one, the area is what? 2 times 9, okay, which is 18. Therefore, part two, the area is what? Half 9 times what? 3, which is the height. All right, and that'll give us what? 9, 3, 27. 27 divided by 2 is what? 13.5. Okay. So if you add these two together, 18 plus 13.5, and that'll give us what? You get what? 31.5. So this is, sorry, this is equal to 31.5 kilonewtons. Okay. So we have two options when finding vertical forces, either to break them into two, which I think is an easier approach. All right. And then you go with the moment as well. Okay. So with the moment, so moment is what? Force times distance, right? So here you found the forces. So these are you found the forces, all right? Now let's find their moment arm. The moment arm here will be half of 9 for the rectangle, so it becomes 9 over 2, which is what? 4.5. Then this guy here becomes 2/3 of 9. Okay, which is what? 18 over 3, that'll give us 6. Okay, so it means that we have to multiply 18 times 4.5, then plus 13.5 times 6. Okay, so 18 times 4.5 will be 81, and then 13.6 times 6 will also be 81, I believe. 13.5 times 6, sorry, will be 81. So that'll also be 81. Okay, and this is why I had these two 81 values over here. Okay, so that's all, that's right hand, I mean, this part one here is the same as everything in the space, and then the part two here is the same as everything in the space as well. All right. So at this point, it becomes like a geometry problem, finding centroids, finding areas and stuff like that. Okay. During your tutorial sessions, I'm sure you might serve as an example on this, and maybe have the shear force and bending moment diagrams drawn as well. All right. Let's just stretch our legs for like five, please, only 5 minutes. Because we've already spent some time with the whole issue that we had earlier. So spend 5 minutes, stretch your legs, and let's come back and continue. Okay, let's take a break for 5 minutes. Yeah, so we're back from our break. Um, so just to take a note, you already have lecture notes on the topic we've been discussing so far, like written lecture note, properly typed, and then all of that. And I think there's an example, a very long example at the very end of the lecture notes with a table to show how some of these diagrams will look like when you draw them, all right? I would advise that we spend some time to go through these notes and also go through some of the calculations in there because they explain further some of our discussions that we've been having in class so far. So let's move to an entirely new topic. Not new, but I mean something entirely different, okay? So we have a new lecture today. I'm just going to introduce the topic to us and then we can continue next week. We are looking at the analysis. Uh, hope I'm recording. Let me just check. Okay. Analysis of what you call pin jointed frames. Okay. Into bracket trusses. Um, so let's look at what trusses are. You've seen them. You've seen some examples of it already. Um, so in defining trusses, um, typically it is composed of what you call slender members. So when we say that something is slender, it means that if you compare uh, the the um the thickness of that particular member is very small compared to the entire length of it. Okay. So for example, you guys might have come across this when you were on your field trip. Just trying to show you something. You might have come across these steel members, right? Um, we call these are what we call the angles, the name given to this type of, because they have this L shape, or maybe some might even call them L shaped. So they are quite long, very long. And then if you look at how they are, because they are quite thin in terms of the thicknesses, they tend to bend, all right, easily tend to bend when you apply loads to them. So is the reason we call them slender members. Okay. So they are slender members. That is one. Two, these slender members are usually joined together. So join at the ends by pins. Okay. Um, so we could have a series of these members come together. All right. And then we assume that at the point whereby we are joining them, this point here, we assume that this joint is made as pins. Okay. When you went to the site, I think at Apollonia, where you guys went to look at the steel structures, right? What you guys saw was what you call a portal frame. Oops. Yeah, hello. Can you hear me now? Sorry. Okay, great. So let me go back. All right. Um, So we are looking at the analysis of pin jointed frames. All right. And there are also some other type of frames that we have. And the pin jointed frames are frames which are pretty much a combination of slender members, which are joined together at their ends by hinges or pins. All right. And we define a slender member as a member that has a very small thickness compared to the overall length of that member. So here we have a steel member, which is an angle or L-shaped member. And if you look at the thickness of it as compared to overall length, it's quite small. All right. And such members, when you apply load to these members, they tend to buckle, they bend. All right. Um, so I was saying that when you guys went for your field trip, you would realize that I think at the Apollonia, what was the name? The Apollonia site, you had some, I think it was a warehouse that you guys went to see or so. Or maybe, I don't know what you guys saw, but you had, oops, you had your buildings, the frame system looking like that. Okay. So we call this a portal frame, for example, right? And then they are joined at these ends. Okay. So the joints can I typically they are what we call pin joints, right? Because it's a frame system. It is a truss system. They are joined at these ends, and this could be either through bolting or welds. Okay. But most of the things that I'm sure you guys saw was the bolts. I wasn't there, so I'm not really sure what you guys saw, but I'm guessing that it was bolts that we saw. All right. Um, so usually when it comes to so this is an example of, let me just show it to you guys. All right, so this is an example of frame connection, or in this case, a penetrating frame connection where you have, so this here is what you call the gazette plate. Okay, so the gazette plate is welded to the column. So this is your column, or maybe some other whatever, or some other member. So the gazette plate is welded to maybe the main member. Then you have these other slender members connecting to the gazette plates using the bolt. So these are the bolts, right? So these are how we represent pin joints. So we assume that at the connections, uh, the behavior is like a typical hinge, right? So it's either uh, pins or hinge. We mostly just say pin joints, right? All right. So the behavior is a pin system, and they are commonly used for roofs. All right. So we have roof trusses. Um, and also bridge trusses. All right. So here's an example of a roof truss with some critical information available to us. Hopefully this thing should load quickly. It's taking forever. All right. Should be in. All right, great. So this is a typical example of a roof truss. Let's look at some of the key part of it. So we have our roof here. And then this system over here is the truss system. Okay. So these are the connections at the ends. All right. And then we have these being the members. Oops, but okay, it wasn't really work. I'm just trying to figure out. Okay, so these are the members, the different members that we have. All right. So we could label them. So usually when you have a roof, this is what's happening to my screen. Okay. When you have a roof, this is what we have. So normally you have something like this. That's not the best way to draw it. Just trying to figure out how to get this thing well drawn. Um, let me see if I can get an example. So maybe this should help us. Let me. Okay. Uh, okay. Back. Yeah. So we have a series of roof trusses. Okay. So this is like one set. Just to explain to us. So this is one set. It's not my pen is not too clear. Maybe let me make this one bigger. So this is one set like this. All right. Then there are others also behind. So like the series of triangles, as you can see them. So we have these series of trusses. All right. Okay. So that's how basically how trusses look like. And then we place our roof as a what's the name? The sheet on top of the trusses. All right. So whatever we see in this space, right? There are a series of them that go along like that all the way to the end. And then we have uh, a wood or a metal piece lying on top of it. Okay. So we call this wood or metal piece lying on top the purlins. And that's what uh, holds or that's what we nail the roof to. All right. So we have a series of these types of trusses. All right. And they have different configurations, right? Or different shapes that they come in. Um, the key thing about pin jointed members is that the members themselves cannot transmit moments. Okay, which I would explain a bit more. All right. So we have different types of configurations of the truss system. So for example, if you're looking at the roof truss, um, right. So the ones used for roofs, an example could be this setup right here. So we have what we call the Caesars, we have the Cambet Fink, we have the Hawaii, and also we have the Warren. There are other types that we have. Um, we also have the Prats and the bowstrings, the fan. Let me see if I can bring them up here. This should show any moment from now. So here are more examples of the types of roof truss that we have. Okay. So here's the prat. This is the sawtooth. This is the fan. This is the bowstring. Then we have two more, the fink, and then the three-hinged arch. Okay. Now, when you go to the Trinity Hall, where you guys have your church services, when you look at the ceiling, oh, I'm sorry, the roof, it's not really any ceiling. When you look at the roof, so you have this arch-like shape, all right? Metal, I think it's sea blue in color, like a series of them, right? And then you also have an, if I'm not mistaken, another second one, whereby they are joined in this form, all right? So you have something like that, and then the roof will sit on top. So the roof has this curve-like shape, just like the way the arches. So here, this is an arch plus truss system. Okay. We will look at arches later, but basically the whole zigzag arrangements, which I've drawn with the green here, is the truss system, which connects to the different portions of the arch system. All right. And then they'll all end up with a support at the very end. Okay, so you see this large support. Anytime we try approaching the Trinity, or you see this very large support at those ends. Okay. There's a reason why the supports are that large. We'll look at those when we're looking at arches later. Okay. So these are the different configurations of trusses that we can have. All right. Um, the general idea is that when you have a truss system, let's say, for example, if you take the fan example, there should be some beams or columns that will support the truss. So in this case, a roof truss. Okay. So then these becomes the supports. They can act at the ends or they can even act in the middle. It depends on what we are looking at. All right. Or whatever case that might be. Okay. So here are examples of roof trusses. Now let's look at what's the name? Bridge trusses. Some of them are quite common. I think at the beginning of the course, we looked at a bridge, a typical bridge to understand an example of a truss. Okay. So here we have a bridge truss. All right. So again, if I take this portion here, can I, oops, this is bad. So I have this, the, okay. So as you can see, if I'm to draw this again here, I have, then these are my supports. So here's a ruler, and then this is a pin support. Okay. So this is a typical truss or for a bridge. Okay. Um, we'll look at the different types of trusses in terms of how to analyze them. But for now, I'm just trying to explain to you guys what some of these trusses are used for. All right. In this case, for roofs and also for bridges, mostly. All right. So with a bridge, you can see that we have two main trusses. So this is one, and there's also this second one on the far left, and then they are joined together with a series of floor beams, a series of what's the name? Portal bracing, and then all of that. And then we have our deck on it. So the deck is where Um, oops, it's where the vehicles will pass on. All right. So we have again we have different types of bridge trusses. I'm showing some examples. So here's these are some examples. Again, they have similar names to that of the roof, but these design configurations are adopted when you are looking at a bridge, right? So typically for bridge trusses, you might have one or two or three of these trusses. So there'll be another one or maybe on this side, which then will be connected uh, by a series of what's her name? A series of top chords so that you have something like that. Okay. Oops, this looks interesting. Right. So there could actually be three of these. Okay. Or maybe two. Okay. So that's how they are formed. And then here becomes the deck on which the vehicle should pass on. Okay. So you have different configurations. Some of them are named after the engineers who came up with these concepts, right? So the Pratt, the Highway, the Warren, the Parker definitely would have been named after the engineers that came up with this concept of truss systems. Okay. There are a few more shapes out there, and every day new shapes are being developed. But most of the time, we just go with these older shapes. Then we also have on the right, there's a Baltimore, then the subdivided Warren. They also have the K truss. Okay. Again, different configurations of truss that we have. Okay. Um, so when it comes to trusses, um, the key thing that what the members are pin jointed. So if I have this here as my truss, all right, let me label them A, B, C, D, E, F, G, and H. The joints here are pins. Oops. Okay. So for this type of structure, we have how many joints? One, two, three, 4, 5, 6, 7, 8. So let's say the joints here are 8. Right. So now let's count also the members. So a member is connected at the ends, right? So we have here member 1, member 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 13 members. Okay. So let's say there are some supports at these ends. All right. Okay. I mean, for we to call an object a structure, it should have supports, right? It should be able to transfer the loads to some other member or to some to the ground or somewhere. All right. So again, when we take these members, okay, before we start looking at the member behavior, uh, let's look at the overall structural behavior first. Just like how we did with the beams, all right, so that it follows that sequence. Okay. Now we need to also classify the structure or the truss, all right, to see whether it is statically determinate, indeterminate, or otherwise. Okay. So let's say statistical classification uh, of trusses. Okay. So you have three main types. It's either it is statically determinate, which is what we call a perfect frame, or it is statically indeterminate, and then we call this a redundant frame or a frame that has some redundancy. All right, redundant frame. Then you also look at what you call uh, unstable truss, right? When it's unstable, and then we call this a deficient frame or truss. Okay. So if you see me use the word perfect, I tend to mean that it is statically determinate, or if I use the word redundant, then it's statically indeterminate. And then when we say it's unstable, it means that it is indeterminate. All right. Oh. So let's understand what these are. Now we know what a joint is, right? It is the point where the members are connected. We know what the members are. And also we know that once there are supports, there will be what is happening? Once there are supports, there would be reactions. Okay. So we should have some reactions over here. Let me call this VE, HA, and then VB, sorry, VA. Okay. So our known reactions, unknown reactions will be equal to 3, right? At least to explain what we'll be doing shortly. So if we want to determine the whether our structure is statically determinate or otherwise, we have a series of things to look at. Our equations E, which I'll explain shortly, E is equal to 2 times the number of joints. So the number of joints, let's call that small letter J. 2 times the number of joints. Then our total number of unknowns will be equal to the unknown reactions R plus the number of members M. All right. I want to go to All right. So when your E, so um, when E equals J, then your structure is statically determinate. All right. And then, sorry, E equals U, not J. So when E equals U, then the frame is statically determinate. When U is more than E, so I think preferably I do when U is equal to E. So if U is more than E, then it's statically indeterminate, or it is can you hear me now? Um is my voice back? I'm told you cannot hear me. Is it better? Okay, all right. So let me go with the classification again. All right. So just like how we had with the moment resistant frames, I mean the beams that we looked at previously, with trusses, we also need to determine or also classify them to see if they are statically determinate or otherwise. And to do that, we look at a few options that we have. One is to know the number of joints that we have, also know the number of members that we have, and also determine the or know how many unknown reactions that we have. Okay. Um, so that if we want to know the total equations, we multiply the joints by 2. Then also, if you want to know the number of unknowns, total unknowns, we add the unknown reactions to the members, right? And then we find E and U, where E is the what's the name? The total uh reactions, and then so let me call U number of unknowns, and let's call E equations of equilibrium, or equilibrium equations, the same thing. All right. Okay. So if U equals E, perfect frame. If U is more than E, uh, redundant frame. And then when U is less than E, then it's a deficient frame, or a frame that can easily collapse. Okay. So let's look at some examples to explain. If you have this frame system, okay, these are your supports. All right. So now let's count our joints and see. So we have joint 1, joint 2, so 1, 2, joint 3, and then joint 4. So there are 4 joints. The number of joints, J, is equal to 4. Let's count our members. Member 1, 2, 3, 4, and 5. So our members here, M, is equal to 5. Now our support reactions are 3. All right, so 1, 2, and 3. So reactions R is equal to 3. Great. So our E here is 2 times J. So 2 times the number of joints, and that'll give me 8. Okay. My unknown reactions is R plus M, and that'll give me 5 plus 3. Okay. So since U is equal to E, this is a perfect frame, or it is statically determinate. All right. Um, okay. Now let's look at another example of a statically indeterminate frame. Okay. Am I correct? Let me see. Okay. So let's say again I have the same frame. Let me just draw it here to make my work easier for me. So I'm going to pick the same frame over here. Just copy and paste. Okay. So let's say I add another member. Oops. What was that for? Okay. Let's say add another member. Okay. So let's call this member 6. So they are not intersecting. They're just passing by one another. They're not meeting at a point. There's no joint. So there's no joint here. No joint here, right? No joint over there. Okay. So what is going to happen is that our joint will still be what's the name? Will still be 4, but now our members have increased to what? 6. Our unknown reactions are still 3, which means that our E will still be 2 times J, and that'll give us 8. And then our U will still be what? Uh, R plus M, and that'll be what? 3 plus 6, and this is 9. So because U is more than E, the frame, um, or our frame is what? A redundant frame. Okay. What this simply means is that you don't necessarily need that extra member, right? Member 6 is not needed. The frame can work as we've seen with the above perfect frame. The frame can still work. It can still transmit the loads without failure. But what the redundant frame serves us is that should there be any failure of any of the other members, let's say maybe um, member 6, sorry, let's say member 3 fails, for example, for one reason or the other, if member 3 fails, it means that member 6, which was initially useless or redundant, now takes up the what's the name? The responsibility of now being the one to carry the loads that were initially being carried by member 3. Okay. And in design, we would prefer to have a bit of what you call redundancy. Right. Um, you've heard this term a lot when it comes to jobs, right? Where they go like some people became redundant and then they were asked to go home. What it simply means that what they became surplus to the requirements of the workforce. Maybe the company felt like they needed only 10 people to do the job, and then there were 12 people. So two of them who will not adapt to anything have been asked to come home. They are redundant, they are surplus to the requirements of the job. But sometimes, even in companies, you need that surplus because let's assume that maybe there are 10 people who can do the work efficiently, and then you hire 12 people. So it means that there are two more people who are not really needed in the company. But this what happens. Let's say one person falls sick or is not able to come to work for one reason or the other. Now, out of those two extra people, you can have one person do the work of the other person. All right. Again, if two people fall sick and don't come to work, now these two extra guys who were initially surplus to requirements can now fill up the role of those other two, and the work can continue efficiently. In the same way, we have that with frames, whether uh, moment resisting frames or whether it's pin jointed frames. We include what's the name? Uh, we include these redundancy that in case there's any failure of one or more of the members, that these redundant members can take over the load carrying capacity of the structure. Okay, and by so doing, they tend to reduce the incidence of failure. Okay, so let's take a note of that. Then we have what you call the deficient frames. So I'll just paste this over here as well. And then, okay, I should have looked at my labeling properly. Maybe I should have actually label this. Let me change this a little bit. Let me make this one. This one is 5. This one is 4. Okay. So let's take away this guy. So now this is our frame. Okay. So again, going back, our joint still remains 4. Now our members have reduced from 5 to what? 4. Our reactions are 3. So again, E is still 2 times J, which will be equal to 8. But our unknowns have now reduced to what? 4 plus 3, which is what? 7. So now U is less than what? E. And this makes our frame deficient. Okay. And when you assume that you apply some horizontal load to this frame, it will collapse. It would collapse because this is an unstable frame. All right. So when it comes to pin jointed members, you first have to identify whether it is a perfect frame, whether it's redundant, or whether it is deficient. Okay. And it's important to find out which is which. And also, um, when dealing with trusses or frames, please, in this case, anytime I say frames, I mean pin jointed frames or trusses, right? The same thing, right? So when you are dealing with trusses, the simplest truss is a triangular truss. So the simplest truss is triangular. So this is the simplest truss. Okay. So you have this and that. Okay. Here we have how many joints? Our joints are 3. Our members are 3. Our unknown reactions are also 3. So E is equal to 2J, which is 6. U is equal to 3 plus 3 for M and R, which is equal to 6. So this is what? Perfect. All right. And this like in this simplest form, this will be the perfect frame that we have. All right. So normally, if you want to increase our frame system, we tend to add triangles. All right. So always add triangles, add triangles, add triangles, and stuff. So as you add triangles to it, you still maintain the perfect frame system. All right. That's the way we usually do trusses. All right. So normally we could have 3 main trusses in terms of how they are organized. It's good we get to know what these are. So basically what we are looking at here is the simple truss, right? So let me call this simple truss. All right. And then we have what we call the compound truss. With a compound truss, you are it's trying to combine one or more or it's by connecting one or more simple trusses together. Uh, so let me put here compound truss. Connect two or more simple trusses together. And then you normally use to support loads uh, over very large spans. All right. Um, so an example would be, for example, if I have, let me say I have this. So this is one. This could be, well, this doesn't look right. Let's say we have, okay. So this is like a simple truss, right? Just a series of two triangles. And then I take the same, so I also have another same thing over here on this side, trying to make sure that they look similar. Okay. Oops. All right. Then I join them together this way. So it's like I have on this end a simple truss and then another simple truss together being joined to form a compound truss. All right. This is cheaper. So this is cheaper to construct than trying to do one large simple truss. Okay, so here it says a one large simple truss. And then, so this is a simple truss. While this is a series of simple truss being joined together, and that will form a compound truss. So cheaper. This is a compound truss system. Okay. They also have other types. We have the what's the name? The complex truss systems. And usually, if you have a truss that you cannot define into either compound or either simple, then that truss will fall under complex. Okay. So I showed an example of it earlier, and usually they will have some bit of redundancy in them. So for example, if you have a truss that looks this way, do I have what I want it to look like? Let me see. Maybe something like this. Right. So these are okay. So mostly I'll show you these as well, just so that you know whether they are connecting or not. So I have this other guy here. Oops, no, wrong color. So I have this gentleman here, the gentleman there, and I have here this maybe the supporter I be here and there. All right. This neither falls under, I mean, it doesn't fall under simple, it doesn't fall under compound. So we can say this is what a complex truss. Okay. Most of our questions for this particular term will be focused on compound trusses and then simple trusses. All right. So the key thing will be to what's the name? The key thing will be to determine the support reactions for a truss and also find the forces in the members, right? So we do know, at least from what we've been looking at so far, when we looked at um the bridge, I mean that truss system is what a three-dimensional truss system, right? It is in reality it's 3D, but mostly we assume that we are looking at what a two-dimensional system. All right. So that's how come we have this over here. And we call the two-dimensional system as what? Plane trusses. Right. So trusses which tend to only act in the X and Y directions. All right. We can also have space trusses, which act in both X, Y, and Z directions. Okay. If we have enough time, we might look at the space truss. But for now, we'll be focusing on the plane trusses, which are acting in the two-dimensional um, directions, X and Y. Okay. So just take note. So we have plane trusses. So this is in the X and Y directions or two directions. All right. And then, so an example is what we've been looking at so far. So we take a 3D and then we convert that into a 2D. All right. And then with the space truss, so that'll be a three-dimensional space truss. So for example, you have a truss this way, one comes here, one comes there, maybe there's something like this. And there's one here this way. All right. So in reality, this it looks like this like in reality, well, you have the Y directions, you have the X, you also have the Z directions. Right? So basically, it's a truss systems which you join together to form a three-dimensional structure. Um, so we'll look at that if we have time. We'll look at how to analyze space trusses going forward. All right. Okay, so it's 1:16. We should end at 1:30 then. Okay. So we should end in the next 15 minutes. So let's look at oops, let's mess it up. When it comes to the analysis of pin jointed frame, there are a few things we need to focus on. All right. So analysis of let's say trusses. Uh, we make some assumptions. All right. It's important that we make some assumptions. Okay. These assumptions are that the ends of the members are pin jointed. All right. Okay. So they are hinges. In reality, you don't have a perfect pin joint. All right. There'll be some small element of moment over there. But for analysis sake, we assume that all the ends are pin jointed and that the loads we apply, the loads only act at the joints. So the loads do not act on the members itself, the loads act on the joints. Please take a note. Then the self-weight is negligible, or we are not taking into consideration the self-weight of members is negligible. So, so you're not taking into consideration the weight of the members, all right? And also the cross section of the members. Uh, cross sections of the members are uniform. Okay. In second year, we'll change some of these assumptions, all right? But for now, for simplicity's sake, all the members are the same cross section. Okay, nothing is different over here, right? So our first thing that we need to look at just and over here is to determine support reactions. All right, so just like how we had in the beams, before we find internal behavior, we need to know what external behavior would be. So that if you have this, all right, so I'm going to take away this 1, 2, and 3 and stuff. I don't need them anymore. Oops, but I've deleted. Okay, so let's say I have this here as my structure. These are my unknown reactions. So this is A, B, C, D. Okay, let me call this length here L1. Call this length over here L2. Okay, let's say I have these loads. Let me call this load P2. Call this one here P1. Right, so these are loads acting on the joints. Okay, and I want to find my reactions. So I have my HA, my VA, and my VB. I want to find these reactions. Okay, and this is when you are dealing with with trusses. This is where your good understanding of moments, directions come to play. All right. So I'm doing everything with a free-body diagram. Okay, showing you where the reactions are going to be and all of that. Okay, so when you are finding the external reactions, okay, we'll just finish with this. We need the 3 equilibrium equations. Okay. So we start with the summation of forces in the x direction, so lateral forces, to be equal to 0. So here we have 2 of them. We have our HA and our P1. All right. So take note, HA plus P1 equals 0. They're both in the same direction. All right. So HA will be equal to minus P1. Okay, which should be in kilonewtons anyways. Okay. Now when we sum vertical forces, again we have VB, VA, and then P2. All right. So VA is upward, VB is also upward, P2 is downward. So that will be negative equals 0. So VA plus VB equals P2. Okay. So now we have one equation with 2 unknowns. Normally, you know what P2 might be. I mean, you'll be given P2 anyways. What we don't know is VA and VB, right? So because we have one equation with two unknowns, you need an additional equation to suffice, all right? So we need to take moment about one of the points to eliminate one of them. So let's say summation of moment about A equals 0, all right? So it means that point A has now become a pivot, and then we'll look at all the different loads and how they would interact uh, with the point, and then find their corresponding moment. So let's see. Let's start with VB. Where are you? Okay. So let's look at VB. Um, oops. Let's use the black. We have VB times. So you see, VB is acting in this direction, acting upwards. All right. And I want to take the moment about A. So the perpendicular distance between B and A is L1. Okay. So it becomes VB times, oops, times L1. I think something is not right. Okay, that's fine. VB times L1. All right. And that will cause a counterclockwise rotation about A. Okay. Now we have another load P2. Okay. That becomes P2, and P2 is acting. Let me just redraw this quickly. I'm just gonna so we have P2 acting over here. I want to find the moment about A. The line of action of P2 is this. So this is a line of action, okay, of P2. So the perpendicular distance between A and the line of action of P2 will be the same as what? L1. Okay. Now, if you hold A and then you push P2 downwards, it will cause your truss to rotate in the clockwise direction. All right. So it becomes P2 times L1 in a clockwise direction. Okay. Now we have P1 also. P1 is acting at D and it's going towards the right. It's, it's also going to cause a clockwise rotation about A. All right. And the perpendicular distance between P1 and A is this distance here, which is our L2. So it becomes P1 times L2, and that'll be clockwise. So all of this is equal to 0. So it's up to us. Sorry. It's up to us. You can make this a positive, negative, negative, or vice versa, and it will still work. All right. Now, for HA and VA, because they are all passing through the point A, the moment due to these loads will be 0. Let's take a note of that. Okay. So here it means that our VB will be equal to P2 L1, sorry, P2 L1 plus P1 L2 over L1. Okay. So let's say we don't want to find moment about A, but rather someone will prefer to find a moment or some moment about B, which is equally fine. So it's either this or that, one of them. All right. So if that is the case, then it means that we need to look at the moment due to the different loads all over. So we will end up with so here we get VA times L1, and VA about B will cause a clockwise rotation. Okay. Then we have HA. So with this one, this is what I have, sorry, and I'm just drawing over here. Okay. I have my HA. This is my HA. Daddy. So here we have the HA and want to find a moment about B. All right. Now the line of action of HA goes through B. Right. So because it goes through B, the moment due to HA here is 0. All right. So let's take a note of that. So that will not really count in our calculations. VA also passed through, sorry, VB also passed through B, so that is 0. Now, if we take P2, P2 is acting here. This is our P2, all right. Now, the line of action of P2 is also passing through B. And because it's passing through, the moment due to P2 will be 0. Okay. So the only one we are concerned about will be what? P1. Okay. And if there's the line of action of P1, then its distance at 90 degrees would be what? Our L, the L1 or L2 will be our L2. All right. So it means that VA, that we have P1 times L2 equals 0. And that also be a clockwise rotation about B. So they both will be positive. Okay. Which means that VA here will be equal to minus P1 over L2 over L1. So this should be basically what we can look at in terms of dealing with what's the name? How to find reactions, right? Okay. All right, so we would end here and then we'll continue later.